Good afternoon and welcome to the next session of the day, an interactive visual history of the normal distribution. Our presenter today is Professor Zachary Beamer from Piedmont, Virginia Community College. If you have any questions for Professor Beamer during the session, please feel free to enter those into the chat at the bottom of the Zoom room screen, and we will address them at the end of the talk. On that note, I'll hand it over to our presenter.
All right, thank you, Julia. Let me go ahead and share the PowerPoint that I have here. And I'm going to be hopping in and out of this PowerPoint because I also have a whole bunch of visualizations that are really the heart of this thing and kind of what prompted me to do this. So we'll go ahead and get started with the slideshow here. So I will start off with the introduction. I'm Professor Zach Beamer. I've been teaching at Piedmont, Virginia Community College since 2013. And I teach a big array of courses, a lot of time spent teaching Calc 1, Calc 2, Calc 3, but as well as some of the transfer level math courses as well. I've been doing a ton of stuff with co-requisites, wrote a whole dissertation on it, but this particular talk has nothing to do with those things. This is really getting into one of the real hearts of the things that we talk about in statistics. So statistics, believe it or not, is actually one of the courses that I don't get to teach on a very regular basis. But I was really interested in it by way of calculus, actually. So while I was teaching, so kind of a little bit of background for what the plans are for today and what prompted me to develop this talk for today. I'd like to introduce the binomial distribution, which I imagine a lot of people here have seen before, but if it's been a while, we can review it a little bit and talk about how that binomial distribution relates to the normal curve that we are so accustomed to seeing, that bell curve that's the heart of statistics, where all of the data falls within a certain range of the mean, and that spread of the data is dictated by the standard distribution, or sorry, excuse me, the standard deviation of that distribution. But in addition to that, oh, sorry, can you hear me?
It's just showing like the toolbar, basically the top of the PowerPoint.
That's
toolbar.
Weird. That's weird. Let's try again. Are you seeing it now?
Okay, so now we're seeing like the PowerPoint program.
All right.
Yeah.
We'll just do it without the presentation bit, and I guess I'm gonna try one more time to see if it here. So if I do that, is it now invisible?
Yes, it's working now. Thank you.
Oh, it's working now. Okay, great.
Yes.
Okay. Mm-hmm. Wonderful. Okay. So this presentation also kind of coincides with a paper I'm currently in the process of working on and submitting to a journal in the Mathematical Association of America, because they have something that specifically focuses on history that also builds in a lot of interactives. So that's kind of what prompted me to kind of delve a little bit more into the history. I am not a historian of mathematics, but I found some of this stuff kind of interesting as I've been learning about it. And the big thing that I think is just so neat with all of this is just all of the connections that we can draw between statistics, probability, and calculus. While we don't necessarily have the opportunity to explore all of these in the day-to-day classes that we teach, there are a lot of ways in which we can build in some of this stuff into statistics or in Calc 1 or multivariable calc as well. And the other big motivation for this, when I was teaching online last year, a Calc 3 section, I had my students explore interactive visualizations and what they can do to teach concepts in multivariable calculus. And I was completely blown away by a student who went really above and beyond creating something that visualized the bivariate normal distribution using GeoGebra. And I was so blown away from it that I just had to figure out, how can I make a talk just to show this amazing work that the student had done. She was not able to join us in this presentation today, but I have a huge debt to her because she did some amazing things. So just some historical origins to the normal distribution. So the first time we encounter anything related to the normal distribution here is from Abraham de Moivre, a French mathematician who worked on it in 1770 and 1773, which came about in the symmetric binomial distribution. Let's talk about that for a second. What is the binomial distribution? Well, we can think about it as if we're conducting some experiment where there's a given probability of success, and we're just conducting repeated trials of this. So the very classic example of this would be something like a coin flip. One of these things is called the Bernoulli trial, named after another famous mathematician. But it could be that the probability of success, like with a coin flip, is 1/2. It could be another number, like say, what's the likelihood of getting a 6 when rolling a 6-sided die, for instance. And this is one of those things that we can develop a formula to compute how likely is it that you're going to get a certain number of successes given the number of trials that you conduct, because it all comes back to combinations, right? So if we remember combinations, what we might call N choose R, and there's a dizzying array of different notations for this. But the idea behind N choose R is we're trying to figure out how many, if we have N objects, how many different possibilities are there for choosing R objects from that if we don't care about the order. So you may or may not have taught one of these things in one of the classes that you have taught. We used to teach this back with Math for Liberal Arts when we still had that one. It still comes up in things like discrete math as well, if you have a chance to teach that class. So if you're thinking about, you're flipping 3 coins, right? What are all the different ways in which you can get 2 heads to show up, right? You could get them both at the beginning, you could get one at the beginning, one at the end, you could get 2 at the end. And then the math gets more complicated as if we think about, well, what if we flipped it 10 times and we want to figure out how many possibilities are there to get 3 heads show up. So fortunately, there's a nice formula that allows us to compute that. And then we can add a second element to this, which is if we're thinking of this in terms of the context of some probability, we've got a probability of success P. So we want to have R successes, and that means the rest of them are going to be failures. Well, there's a nice little formula for this, so we can parse it with our fancy math notation here. The probability that we get a discrete random variable, the number of successes matching a certain value, can be found by taking this combinations here, getting R successes. So we're going to multiply, we're going to take P to the power of R, and then we're going to multiply that by the probability of failure, 1 minus P, and take that to the N minus R, because that's going to be the number of failures. So this is a nice little formula that produces the likelihood of getting a given number of successes in one of these coin flip like scenarios. And this actually, knowledge of this formula dates back even further. It dates back to the 17th century, but from a discussion of Fermat and Pascal, something I just learned about today when I was looking this up. But as I promised, I'm not just going to talk at you. We have a interactive visualization. This is one that I built, which is the result that de Moivre came up to, which is that the probability of deviating from the mean by a certain amount could be given in terms of the exponential function in this formula that looks a little bit unwieldy, but maybe slightly familiar if you've done much work with the normal distribution. So I'm going to click on this thing to take us to a separate, excuse me, let me make sure I'm sharing the right thing here. There we go. So here I've built this thing. One of the great parts about GeoGebra, it has a lot of pre-built-in things. If you haven't played around with it, it's got some great functionality, much like the online calculator Desmos. One of the things that GeoGebra does is it can actually give you the whole binomial distribution. So I didn't really have to work hard at this one at all. It built this binomial distribution for me based on a certain number of trials. So let me separate out the curve that we know and love. But as we can see, as we increase the number of trials, the thing that ends up happening is we get this symmetric shape that is centered around the mean, right? So for instance, when we have, say, 40 trials, if the probability of success is 1 out of 2, we would expect to see 20 as being the most likely outcome in terms of the number of successes. Here, if we go over that, we do in fact see, you can kind of maybe see that number there, that if we run it 40 times, the most likely outcome is that we'll get 20 successes, and there's around a 12.5% chance of that happening. If we go slightly to either side, we see that kind of diminishing a little bit. So still around a 12% chance of like 21 successes, and then gets down to 10% for 22. And then the further and further we go out, we have a little bit of this inflection point that we see here. We get to a spot where once we're out to say 27 successes, it's considerably less likely. It's only about a 1% chance. And then it's very, very, very unlikely that we would get even more than that. If you take it to 30, you're looking at less than a 0.1% chance that you would get more than 30 heads when flipping 40 coins. Or actually, rather, that is just 30 heads. But if you go further than that, right, that's the sort of question that we're interested in a lot of statistics courses, is that number is really vanishingly small. And the thing that we're going to be talking about next is how this binomial distribution can be modeled rather well in terms of an exponential function of sorts. So coming back here to our PowerPoint, let me come back. So this is also just a historical side note. This is de Moivre's first work here was actually the first version of the central limit theorem that we can find anywhere in the history, but it was actually kind of beyond his time in that he didn't even actually realize what he had done. It took another close to 100 years before someone really knew the value of his work that he had. The other thing is that de Moivre didn't actually realize the curve that we can now represent. That bell curve wasn't really what he was focused on. He was really just focusing on trying to estimate the probability, because factorials can be kind of a pain to work with. The values get really, really astronomically big in no short amount of time. So it's actually Laplace, another very, very well-known mathematician. This is kind of a who's who of famous mathematicians. We might think of Laplace transforms or things like that. Real titan of mathematics. But Laplace kind of took de Moivre's result and really extended it and expanded it to not just where probabilities were equally likely, but for any given probability. And this has a name. It's called the Moivre-Laplace theorem. And that is the contribution that Laplace had, and the other result that Laplace was able to arrive at. It brings us to another concept from statistics that we may well recognize, and apologies that that image is a little hard to read there. This looks really complicated, but what this notion gets us here is that we can figure out the probability of falling within a given data range, or the way that this is set up, we can figure out the likelihood that the data that we find falls within a certain value under some number z. And the way that we can arrive at it is by computing an integral, an improper integral, in fact, an improper integral that there is no elementary solution for. This is one of these things I love to introduce in Calc 2, because it gives us a great example of an improper integral where there is no elementary solution, right? So the best that we can do is talk about numerical approximations to it. It's not just something we can say, hey, Wolfram Alpha, complete this for me, right? But the other reason I bring this up, you might recognize one of the letters there, Z. This gets us the whole idea of a Z-score, right? We're trying to figure out how much data falls within a certain range of the mean. So it could be anything up to a certain value of Z, right? So there's a slight modification on this to get the actual Z score, but this is telling us the proportion of data that lies under the curve on a certain range. In particular, this is starting at the way left endpoint and then getting us up to some fixed right endpoint. But if we're thinking about names of the normal curve, we call it the normal curve, we call it the bell curve, but this actually also has a name after a famous mathematician. And it's named after, of course, someone who already has way too many things named after him, good old Carl Friedrich Gauss, right? So one of the things that's kind of funny about Gauss is that Gauss has an entire Wikipedia article that is things named after Gauss. So I can encourage you to check it out. I only recognize maybe 6 or 7 of them. There's a lot of things, very, again, one of the most prolific mathematicians. Gauss, again, kind of a little bit outside of, the scope of this current presentation, but Gauss did his own work on this. And his work was also getting to that normal curve as well. But his development of the normal curve was actually he was interested in, of all things, least squares. So I won't talk too much about that one to get too into the weeds, but the big idea that we can come back to is that the normal curve is a family of functions, right? It's 2 parameters. So if you know the mean and the standard deviation, then you can develop that normal curve, which is representing that idealized data distribution. So how much data falls within a certain range of the mean in any one direction or another. So I'm going to share one of the, there we go. So there's a bunch of different interactives. I'm going to come in and out of this one because these were all developed from that student that I had mentioned. So here in this second one, we have an illustration of the 2-parameter normal distribution, right? So if we take mu and we adjust it, then that has, of course, the effect of shifting our distribution of data either to the left or to the right. This is kind of a neat thing too, of talking about like the effect of horizontal translation, right? That if we just add or subtract to the value of X, it has the net effect of just moving the graph left or right. One of those things I'm always astounded that my calculus students have seemed to have forgotten from pre-calculus. So this is a nice thing where we can see that shape just sort of migrating to the left and the right. And then the perhaps slightly more interesting variable is if we alter the value of sigma. So increasing sigma means that we're going to expand the spread of data here. So it's going to be more flat, basically. Whereas when we make that sigma value become smaller, we can see that normal distribution really clustering around that, that mean that we see here. All right. I'm going to come back to what I was just mentioning here. So Gauss studied this in a way that is kind of unconnected from the way that we actually did it. So even though he was the first to come up with an expression for the normal curve, he wasn't really interested in it as the way that we are now. It was actually to answer a completely separate question, of all things, least squares regression. So another statistical concept. And when he found that, it was describing how likely it was for to get a certain amount of error based on a random variable. Don't need to get too much into the details for that. But I want to kind of shift gears a little bit here, because when we teach this stuff in a statistics course, we don't get to talk about a lot of the calculus and such behind it. And in fact, interestingly enough, the statistical development of this really came quite a bit afterwards. So we had an expression for the normal curve long before anyone thought to apply it for data in the real world. Something that we ask our students in, a 155 course or a 245, right, an introductory statistics course, we ask them to use a bell curve to approximate the amount of data that falls within a certain range. Of course, we don't ask them to do an improper integral, but that is what we're doing when we're having them look up this table, is we're estimating the value of that improper integral and then using that to model a certain set of data. So it actually was not until well into the 19th century that someone thought to, one, graph it, the normal curve, and then two, to actually use the normal curve to model some set of data out in the world. So I'll show you both of those different ideas in a couple of different visualizations here. So I was reading through this set of historical letters that this gentleman here, let me go back a page, Adolphe Quetelet, who is a Belgian mathematician, which is probably someone that we don't necessarily know about. But I was reading through these letters, which they weren't translated, so I had to brush up on my French to get through it. But he was interested in this, what would happen if you looked at how often, here this is Brussels, how often did Brussels reach a certain temperature on a given day? So if you were to focus it on, say, the month of July, so looking over data over the last decade, in the month of July, how often was the maximum temperature between 11 and 12 degrees? How often was it between 12 and 13 degrees? These are all numbers in Celsius, by the way. And then what would happen if you were to graph what we would call a frequency distribution, right? How often did it reach a certain temperature? Well, it turns out when you graph this, you get a sort of interesting shape, which we might vaguely recognize. Now, it's not perfect because data in the real world, as I try to tell my students, is messy, right? Rarely do things work out as nicely as they do in our textbook examples. Most of the time, data is kind of a mess. So we can see here, while the data does have some, ups and downs, there is that same sort of behavior where there's this tendency that most of the data clusters around actually the mean value of all of the data. And then there's this sort of tapering off where a lot of the data is just not too far from it. And then as we go further and further out, we get this sort of tail behavior on either side. And Quetelet developed this idea further by going back to the thing that we were able to graph using fancy technology. Quetelet did the same thing. He imagined, what if you drew this large number of balls? What if you had 999 balls that you drew from an urn that had an equal number of black balls and white balls? Doing what we would probably in our classes describe as using replacement, which is to say, take one, you put it back, right? So that way the probability never changes from one trial to another. And he ran a whole bunch of numbers, right? Calculations back then were very tedious, but you can run each of those numbers. Again, each of these things can be computed using that formula that we talked about quite a bit ago. And he then had the idea of, well, I'm going to go ahead and make a sketch of all of this. And this image here, which is sometime in the 1840s, is the first time that we see someone actually sketching the bell curve. This is the first instance where someone actually had the idea to sketch that. And I have that same image here. By the way, I'm happy to share any of these links. Some of these things are still works in progress. But one of the things that I was curious about doing was figuring out what would the actual distribution be based on what we know now of how we can use this in terms of the mean and the standard deviation. And I went ahead and computed a couple of things. Of course, the mean number of things that we would expect to draw would be half of the 999. So we have a mean at 499.5. And then the standard distribution, there's a nice formula for it. It actually showed up in a previous slide, that the standard distribution of a binomial distribution can be found. You might know this formula if you teach statistics, by the square root of n number of trials times the probability of success times the probability of failure, which would be 1 minus the probability of success. And if you do that, I went and sketched this. I need to double check my math to make sure I did everything correctly. But when you do that, Quetelet did an okay job, not necessarily perfect. I had to fudge around this thing a little bit with the scale, but there's a little bit of asymmetry to his hand drawing. But again, this is the 1840s or so. So I think we can perhaps forgive the mathematicians back then for not having a perfect sketch. When I try to sketch things by hand, my skills are nowhere near as good as what they had back in the 19th century. It's pretty amazing what they kind of had done back then. So the next thing that I mentioned that Quetelet had been responsible for doing was taking the normal curve and using it to model the spread of data. And again, if you don't read French and the text is too small, I'll just briefly describe what's going on here. So in that far left column, he's looking at the measurement of the chest circumference of Scottish soldiers given in inches. And oops, I lost the screen again. Okay, let me try it. Thank you, Karen. Thanks for coming. Karen is my colleague, appreciate it. So let me know if it's showing up now. Are you seeing it now?
Yes.
Okay, great, thank you. So here we have a table of all of this data that was taken from the Scottish military. They measured the chest circumference of all of the soldiers serving in some regiment at some time. And what he thought to do was to take all of this data and think about, well, how likely is it for a certain individual to fall within a particular range? So if you can kind of see here that most of the data is, again, clustered towards a chest circumference of about 39 or about 40 inches. Most of the soldiers fell in approximately that range. And then as you go either smaller or larger, you see fewer soldiers with a chest measurement of, say, 38, and then even fewer still with 37, even fewer still with 36. And you get a roughly symmetric behavior in this data, that it does approximately the same thing going to the right side as well. So I won't get into all of the details of the table, but he basically then estimates how much data would you expect how much data would you expect to find within a certain range if you estimated it using this sort of normal curve. I won't get into the details of his calculations, but what I can do is show you what the data looks like if, once more, we make a graph out of it. So what I've done here that you might see is graphed the data. So I've graphed all of the data points and how frequently they showed up. I did it in terms of probabilities here. So if you can see that y-axis, it's noting how much of the data fell within a certain range. And again, while he didn't have the advanced tools to sketch this graph, it does turn out, again, when you look at the data here, I'll get rid of that thing for right now. When you look at the data, it does a really, really good job of following a normal distribution. Again, it's not perfect, but it really, really does have that tendency to cluster around the mean. And so in terms of thinking about, well, what's the value of this thing? If you're thinking about like a Calc 1 or a Calc 2 course, this is where we can think about, well, how can we apply integration, particularly in like a Calc 2? So you can find the area under this curve, and if you find the area under this curve, that corresponds to a particular meaning, right? So for instance, I have here calculated the area under the curve between 39 and 40. So using an idealized measurement, we would estimate about 19% of our data to fall within that range, that 39 inches to 40 inches of chest size. And here I also have this set up so you can you can have it go a little bit further to the left and to the right, right? So you can see here with our idealized measurements, I didn't do the things in advance, but we have those standard rules in statistics about the proportion of data that falls within 1 standard deviation or 2 standard deviations of the mean. So you can use this as an actual set of data that does in fact do a pretty good job of following a normal distribution. And so we could then use it to ask even more nuanced questions than Quetelet would have been able to answer using the methods that he had. All right. Now there's one last figure that I want to mention, and hopefully you can see.
Hi, Professor Beamer, the PowerPoint is not showing.
Doing it again. Yeah. I don't know why it chooses to do that. Something weird about it. All right.
It's back up.
Okay, cool. So one more historical figure, and this is perhaps the most problematic historical figure that I will mention. So Francis Galton was a towering pioneer in statistics. So many of the ideas that we talk about in statistics do owe a legacy to Galton. But I'll only briefly mention that Galton's, in addition to being a pioneer of statistics, he also has the dubious notion that a lot of the techniques that he developed in statistics were to justify a rather prejudicial set of ideas. So he is actually also the father of eugenics. So it's impossible to talk about Francis Galton without mentioning that aspect of him as well. And really a lot of statistics in the early development of it did have that same unfortunate aspect. Fortunately, we can still use these methods now for better ends than the forebears, the developers of these had. But here's this nice picture. So if we're trying to think of him as a criminal nowadays, he actually was very interested in things like criminology and the gathering of data to make measurements of criminals and sort of predict criminal behavior. You can imagine where that's led. But setting that aside, coming back to the math part of it, where this idea really goes into the next dimension is through what Galton talked about as regression to the mean. So the subject that he was interested in was the relationship between the heights of adults and their children that they had. So their children as adults. So roughly, we all have this sense that like tall parents give birth to tall children and short parents give birth to short children. But of course, there's always a little bit of variability in that, right? I'm about 6 foot or 6.5 feet. My brother is like 6'2" or so. My sister's like 5'9" or something like that, right? So depending on, just various complicated factors that we now come from genetics, in addition to nutrition and all other sorts of things, there's some amount of variability in terms of the height of children based on how tall their parents are. And just to sort of standardize it, Galton took the heights of any female children or mothers and multiplied that by 1.08, which was apparently a factor to kind of make them roughly comparable to the height of men. But you can kind of see in this table that, so just to try to go by like row. So for instance, here in this column, we're looking at if the average height of parents was 69.5 inches, we see this distribution of how tall on average their children were. And he grouped it into columns that may not make full sense to us, but there's some reasoning behind it. You can check the primary source if you're curious. But basically, we can think about it as most of the kids of parents who were 69.5 inches on average were about 69.2 inches, right? So we see that number 33, that's the largest number. And we see this slight tapering off if we go either to the right or to the left of that, right? So there were fewer children then that were slightly shorter, and then the further and further away we go from that, we again continue to see that tapering off. But there's actually kind of another interesting thing that Galton had observed, and he was the first one to observe this, which is that when you compare the heights of the parents to the typical heights of their children, so that's the last column there, when you had parents who were like rather tall, so 71.5 inches on average, the median height of their children was actually like 69.9 inches. So it was a little bit less than that, closer to a typical height. And we see the same thing when parents had a height of about 70.5 inches, their kids on average were like 69.5 inches. So again, the kids were still taller than average, but a little bit less so. And actually the same thing happened in the reverse direction. When the parents were particularly short, the children that they had were shorter than average, but not as short as the parents when you look at that in sort of aggregate. And the key insight here that came of this is taking this data that we have here and plotting it on an XY axis. And here, this is the cool bit. So it turns out that when you plot the data on an XY axis, a couple of things happen. First, each row and column ends up being approximately a bell curve, basically. So you get this sort of clustering. If you know the heights of the parents, you have a roughly normal distribution for how tall their children are. But actually, it works the other direction. If you know how tall a child is, you can make a guess about how tall their parents were when combined, right? So each of those things, you can draw an inference. Knowing something about the height of a child, you can make an inference about how tall on average their parents were. And not only that, the other thing that's really interesting when you plot it on an XY plane here is that you end up getting this data sort of clustering around in this kind of elliptical pattern. And here, oops, I've got two last things here to share with that. So Galton was a pioneering statistician, but not exactly the best mathematician. He didn't quite have all of those mathematical chops. So he actually enlisted some assistance from someone who was more of a kind of professional mathematician. And here I've embedded that image there just to show how good at drawing ellipses Galton was. I'm jealous of this sketch. But basically, it's an ellipse that's sort of essentially rotated a certain angle. So here's another math concept being embedded, this idea of rotating ellipses, which is something that we do in Calc 2 a little bit. We get to talk about conic sections and like polar coordinates and how do you rotate things. There's actually some even nicer math beyond what we do in that class, rotation matrices. That's how I got to what I did here. But the interesting thing that we can note is that there's some sort of angle that then shows how these two things are related to one another. And that gets us to our last idea, which is the notion of correlation, right? The other huge idea. Now, Galton didn't develop it in this particular paper, but he did develop it shortly thereafter. I won't get into all the details of that because there's already enough information here as it is. Aha, I found the right thing I'm supposed to share. There we go. But getting back to the cool thing that my student built, when you think about two variables that are random and follow a normal distribution, but are related to one another, the shape that you get is what we call the bivariate normal distribution. And it has this particular sort of shape. And this is one of those things that was definitely not the sort of thing that we would have been able to make a sketch of back in the 1800s, right? They could make that 2D rendition of it. But here with GeoGebra here, and let me blow up this one for a second. Here, I've got a 3D version of this. So the expression of the normal distribution in two variables is very unwieldy, but it's also very applicable. Anytime we're talking about two variables that are both following normal distribution, but also related to one another, right? If you look at this thing straight on, so here's where the multivariable calc comes in. If you look at this thing straight on, you see a bell curve. If you rotate it and look at it straight on from the perspective of the other variable, you also see a bell curve. But there's also this aspect of correlation here, which we use the letter rho to represent correlation. So if we adjust the value, so if you have a correlation of 0, you've got what we call two independent variables. They don't affect each other whatsoever. Now, if you scale up that value of rho, you get positive correlation, which means if you know, let me rephrase it this way. If you know what one variable is doing, you have a certain way of predicting what's going to happen with the other one, right? We think about this as representing a cluster of data, right? So when we have a positive correlation, then it means that as X increases, we tend to see this increase in Y as well. The stronger the correlation, the more and more that we see those data sort of falling within a smaller region. And here's where we get the final connection between what we just saw with Galton and what we see with this multivariate surface. Let me X out of that and go on to the last one. And this is something that my student built. I was thoroughly impressed by this. I gave her some suggestions, but she completely ran with it. So it's this idea that if you take a set of data that is correlated and you throw an ellipse on it where it's centered at the two spots where the means of the data distribution are, and you can kind of change the size of the ellipse, but depending on the size of the ellipse, you have how much data falls within that particular range. I won't get too technical in terms of what K means in this context, but the idea is that if you allow yourself, if you want a lot of data to fall in here, then you make this value of K be rather small. And here, let me adjust my values of sigma just a touch here to make it look a little bit more apparent. So when we have this random assortment of data, the height of this surface corresponds to how likely it is for data to fall within that particular range. So when you see this little peak here on that surface, that's corresponding to the fact that a lot of the data is clustered in that particular spot. And if I make the value of K get bigger, that's going to make the ellipse get smaller. So there's a smaller proportion of data that falls within that particular range. You need to make a couple of modifications because the other thing that corresponds to this idea is that if you take that value of K here and you actually take the plane Z equals K, that gives you a horizontal plane parallel to the XY axis. And it will, if you slice the normal surface that we have here, the thing that you're going to form is this ellipse. So this geometric idea of the ellipse that we get when we slice this thing corresponds to this probability idea that when we set an ellipse at a certain height, we will get a corresponding predicted amount of data that will fall within that range. There's a lot more technical stuff that we could get into, but it's 3:45 on a Friday. Thank you for coming as late as you did here. I will go ahead and once more thank Hawks for putting this on. I'll also thank my colleague, Carolina Naranjo, who helped make all of these things. There's a lot of really, really interesting stuff, and hopefully you took away one or two things. I'm happy to answer any questions while we're still here.
If you have any questions, please feel free to send them through the chat below.